Hello and welcome to this video lesson. Today we will be looking at concepts of basic circuits. Before talking about how a circuit works, we have to talk about what is meant by electric potential energy. Before that, we're going to talk about how do we actually create that electric potential energy. So here we have a situation in which we have a piece of fabric, cloth, fur, and we're rubbing a piece of plastic, metal, or something else with it. And by doing this, we're transferring some electrons here. So the force of friction is taking away some of the electrons from the fabric and putting it into this piece of cloth. This is called charging by friction. And in this case, this object here becomes positively charged because now it has a deficit of electrons, and this object is becoming negatively charged because now it has an excess of electrons. Now, if we go and take this negatively charged rod and bring it in contact with a metallic sphere or a conductive sphere, we will get all or some of the electrons from this transferring into the metal. Now, the metal is a conductor, meaning that it's got delocalized electrons. So the electrons aren't really localized to any of the atoms, and they don't really like each other for the most part. Not that they don't like each other, but they have an electrostatic repulsion between them. So the excess electrons here typically is collected around the surface of the conductor. So now what we've done is initially we charged this rod by friction, so we actually put some energy into charging this. That charge went and transferred into this conductor, and now we have this metallic conductor which is negatively charged. Note that all of these electrons at the moment are electrostatically repelling each other, and these electrons in the surface here, they're ready to leave this conductor. They're not really happy where they are, and in a way we say that they have a potential to move and do something. That specific potential is called the electric potential. And let's say now I bring another conductor here, which is just neutral. It's got zero charge, and this one has a negative charge. These electrons are kind of saying, okay, if we have an opportunity, we want to jump over. If you have enough distance, if you bring them close to each other, these electrons will jump. But if they're far enough, they're not going to go because the electrostatic repulsion isn't that strong when the distance is large. Now let's say that we go ahead and bring these two in contact using another conductor. So let's say we got a wire made out of copper, which is also a conductor. Now the potential here, we're not showing it in this specific case, or we're not showing the electric field. As soon as we have this idea over here where we have the electrons ready to escape, these electrons are ready to jump out again in any direction. As soon as I connect it with a wire, there's kind of what we call an electric field here. I've kind of represented it here by these lines. I didn't draw any direction for the purpose of this specific video. But you can see that there's a lot of lines because there's a charge difference of 4 here. So this one has a charge of -4. This one has a charge of 0. And this means that between these two, there's a difference of charge of 4. And that charge creates an electric field between them that's actually quite strong. And as soon as we connect the wire, what ends up happening is one of these electrons, and this is not really an electron, this is a unit of charge, which means there's many electrons. They start moving. They don't want to be here, so they start repelling, and they see that, oh, there's some empty space there. As soon as one of these ones starts to move, and this field over here causes the electrons to really start moving, it will kind of go and push this electron. This electron will push this electron or unit of charge. This set of electrons will move this set of electrons, and these ones will go and jump into here. And now your charge difference starts to reduce a little bit. Now you have a total charge of -3 here and a total charge of -1 here. So one excess electron and and 3 excess electrons here. Now, by this movement of charge and this set of charge that came from this set of wire into here and loss of this set of charges into the wire, the difference between the charges have reduced. We got -3 and -1, and instead of having a difference of 4 in terms of the charges here, 0 to 4 or -4 to 0 here, we have -3 to -1, the difference has become 2. This makes this electric field weaker. And you can see in this one I've drawn the electric field pretty dense. That density has reduced now, meaning that the force or the push of the electrons is going to be less now. So the speed, in a way, or the force at which these electrons are being pushed is going to reduce from this point to this point. There's still some push though, because the electrons here are trying to escape out of here, and the electron here also doesn't like being really the excess electron, so it wants to escape as well. But the difference here, there's more electrons wanting to escape here than here, meaning that one set of electrons is going to go get pushed into the wire, and this set of electrons are going to move, this set of electrons are going to move, and this one set of electrons is going to go here, and at that point we got -2 net charge here and a -2 net charge here. And we got here, I've written that this is the change of electric potential energy into kinetic energy of the electrons, because that potential of electrons or electric charge to move has now turned into the movement of electrons, which we know as kinetic energy of the electrons. So at this point over here, I have -2 charge here and -2 charge here, and that would mean that the electrons are being pushed, trying to escape by -2 here, also -2 here. So it's kind of the same. Electrons are being pushed in this direction in here, and electrons are being pushed in that direction. And the net difference is about 0. So that electric field inside here doesn't really exist as much anymore. Or what happens is being pushed to the left by this one, being pushed to the right on this one. The net effect is 0. So there's no major movements of electrons here. Now, here I've made a mistake in this diagram. So here I actually don't have this charge, but I got a net charge of -2 on both of these cases, and there's no more ones, or there's still some electrons really moving in reality when you make that contact, but there's not a large amount anymore, and there's not much potential, electric potential, that's going to change to the kinetic energy anymore. Now we have an idea about what it means to create electric potential. It means to charge an object and make those charges want to move. And as soon as there's a separation in charge, where one object has a net charge of, let's say, -4, and one has less than that, there is a possibility that if we connect them through a wire, these charges are going to try to go from somewhere which has an excess of electron to a lack of electron, or just less electron. So that potential, electric potential, is created every time we have excessive electrons in one and less excessive electrons on the other. Now let's talk about how can we use this to our advantage. So let's talk about the energy transfers that happen. So in the last example that we had, we have a charged object that we charge by friction. So we put some mechanical energy in there, and then by bringing it to this metal, we create what's called the electric potential energy, which means that there's a charge difference between this metal and this metal, and the electrons here are trying to move out because they're all electrostatically repelled by each other, and by bringing this wire, we're allowing these electrons to move here And from this wire, the charges are going to start moving here. And once we got one set of charge moved from the wire into here and from here to here, this will become -11, -1. So the charge difference becomes 5. And then we will have another one, we will have -10. The charge here becomes -2. And that difference keeps reducing until we get to a situation when we have -6 and -6, causing the net to be 0 now. If I subtract -6 from -6, I'll get 0. Here, if I subtract 0 from -12, I should get 12. So the difference is a lot larger here. So the electric field here is extremely strong. So these electrons and the push is really strong. Here, there isn't much of a push. Now, as we move these electrons through the wire, let's connect the light bulb. And here is a very simple demonstration of what's happening. I'm going to put two little particles. I'm going to represent these two little pendulums here are representing two particles within this light bulb. And as these charges in the wire start moving or being pushed by this charged object, as they move, they bump into these particles. And when you have an object which is moving in this direction and bumps into another object, this object here slows down and this object here starts to move. This is what we call transfer of energy, kinetic energy, or transfer of momentum here. So every time we have a group of electrons hitting the particles of the light bulb, these particles start moving, and as more electrons hit it, they start moving faster and faster. This movement is mostly vibration, so the particles are moving back and forth, and that back and forth motion starts to increase. So what's happening is we got the kinetic energy of the electron or group of electrons turning into the kinetic energy of the particles of the load. And as soon as these particles start vibrating more and more and more, what happens is maybe later on you will learn that the kinetic energy of the particle is proportional to the temperature of the object. So as soon as that kinetic energy of the particles increases, it causes the temperature of the light bulb to increases. This would mean that you got faster movement or vibration, and as the charges basically in the light bulb are moving faster, they're going to start accelerating more, and you can see that as a form of light and other forms of energy, and you also see that as you can also feel that as heat. So the kinetic of the energy of the load also goes to the, so as these particles start moving faster and faster, they can cause the particles on the air possibly to move faster as well, kind of transferring their energy there. And that is also something that you can feel as heat. But most of that energy, since the particles are vibrating, is coming from radiation. And that radiation can be seen in forms of visible light, or it can be felt as heat. So that is the big advantage of how we can actually use this potential or electric potential energy and transfer it into some other form of energy. Now, in this specific case, the weakness of this situation is that as soon as the electrons move from here to here, they kind of stop. At this point, nothing else happens. And also, initially, they will start being forced to move at a very fast pace, but then as the change in the charge situation decreases, the force also reduces, so it gets weaker and weaker. So you will have a situation in which the light bulb is lighting up pretty bright and then eventually it dies down. So the question is, how can we not stop this flow? How can we have the situation in which these electrons don't stop moving from one direction to the other? And how can we keep this light or the brightness constant so it's not dimming down? And to do that, basically what we really need is we need something as soon as one set of charges moves to here to take that charge back to here. So we will keep the difference. So as soon as this charge, for example, goes into the wire, this charge goes into here, something invisible starts moving this back here. So we always keep that charge separations of 12, causing this amount of force, or how fast these charges are moving, keeping that constant, and also giving it the ability for it to move forever. And to do this, we need a battery. A source is able to take some sort of energy and convert it into electric potential energy. In the past situation, what we had was a case in which we were charging one side of this by friction or mechanical energy, and if we can keep doing that, we can keep charging something added here. This charge will become -12. This will then some of the charges will start moving, and then we can keep doing that, which takes a lot of work. So instead, what we use as a source typically is something that can turn chemical energy or sometimes other forms of energy into this at a constant rate. Here's an example of a battery, and what a battery does. There's a lot that goes on in a battery. There are other videos that will explain this a lot better than I can, and they can show a lot more simulation. So I'll try to link one in the video description later. But if I have a battery here, what it does, it uses chemical energy, and it does some reactions which cause a bunch of electrons to be stored in this part of the battery. This part of the battery then, because it's more negative than this side, becomes the negative side of the battery. Typically, when we draw a circuit diagram, this is the shorter side. And this longer side, because it's less negative than this side, is the more positive side. So we say, even though this is not always positively charged, we can say that this is more positive than this one. Positive side, negative side. So the chemical reaction causes a store of electrons here. And as soon as that happens, so what is happening is the chemical energy of the battery is being converted to the electric potential energy of the electrons here. That's causing a field or electric field here that causes all of the electrons to start moving from this side, being pushed out from the negative side and go towards the positive side. Now, as soon as this little, let's say this set of charges move from here to here, I've only drawn 6 here. Let's say each one represents 2. Let's say 2 set of charges move from here to here. As soon as this moves into the wire, this wire pushes the next electron, the next electron, next electron. So as soon as this moves, some set of charges will move from the wire into here. So for a moment in time, this will become -10 and -2. However, this battery will take that extra set of electrons, puts it into some sort of chemical reaction, and that chemical reaction will convert that back into electrons again. So the job of the battery here is to recycle these electrons. So as they move into the external part of the battery, and when they come back, it will recycle it. So you will always have a same charge separation. So always -12 here, always 0 in this specific case. And that causes a constant rate of flow of charge, which we call current, to kind of move from here to here, so that the speed doesn't really change. The electrons are always moving at the same speed around the circuit, and that speed doesn't change. And this happens until the chemicals here can no longer react, and that's when your battery starts dying. That's when, once that starts to happen, when this set of charge starts to move, let's say 2 of them will move, we will get to -10. The charges come here, but this side becomes -2, and the battery isn't fast enough to really bring more electrons here on time. So the next set goes, the next set goes, until we get to the -6 and -6, and that's where there's no more really potential for the electrons to move anymore. Now, it's interesting. If you were to move the battery, let's say it's a dead battery, so it did most of its job, and now you got a -6 charge here, -6 here, basically a net of 0 potential to do any work, and you disconnect it from here. I'm going to draw that here for you. So you got a battery which looks like this, and you got about the same charges here and here. Eventually, what happens over time, the chemicals are still able to kind of move the electrons. They're just super slow. And if they're super slow, they can't really do it fast enough. So once these electrons kind of move back eventually to here, you will start getting these electrons moving from here to here again, so you will start getting the same charge as you did before, and it will still have the same potential. So the potential will be the same again. The potential is you have -12 and 0 here. However, as soon as you connect it to a circuit, and as soon as these electrons will start moving a little bit, they'll move really slow. The battery isn't fast enough to recycle these electrons, so it will die very quickly. So sometimes when you connect a dead battery to a circuit, it will work for a very short amount of time, and then it kind of stops. Okay, a recap of all the ideas that we learned in this one then. We got that the chemical energy of the battery here is being converted to the electric potential energy of the electrons. So these electrons, as soon as that happens, you got a charge difference between here and this side of the battery. You create a potential for these electrons to move. So that electric potential energy, I'm going to add that in, of electrons is being converted into kinetic energy of the electron. So then those charges can start moving. And as soon as they start moving, as soon as this one moves, remember there's a lineup of electrons everywhere in this circuit. As soon as there's a movement here, there's a movement here, there's a movement here, and there's a movement also inside of the load. So the kinetic energy of those electrons that are being bumped into the particles of the light are being converted into the kinetic energy of the particles here, and as they bump into each other. And that kinetic energy of the lower particles turns into other forms such as heat and light. The other idea, kind of we talked about it in this case as well, even if I don't have the light bulb and it just have the battery, because there's a deposit of electrons on this side and there's a net negative charge on this side of the battery, and this side is more positive than this side, the electrons really want to move out. Now, they don't want to move back here because of the chemical reactions that happen, and that's kind of stopping the potential in this direction, but the electrons are ready to move out from this direction. And because of that, there's always a potential for the electrons to move. So the electric potential energy always exists, but it doesn't work until you connect it with a conductor. That's when you really create a path for these electrons to move. And that path is nice, but as soon as you connect that path and connect it to different components, you can convert that electric potential energies into other forms. Now, the light bulb that we just talked about is a component that converts electric potential energy to other forms. So in between, there's the movements and kinetic energy conversions, but what it essentially does, it takes the electric potential energy and converts it into other form. And these category of components that can do that, they're called loads. And so again, load is a component that converts electric potential energy to other forms. And in this specific example, I have 3 different set of loads. All of them have different amount of particles on them. So we have the same battery in all of these situations. On the first one, I'm just drawing this. These pendulums that I'm drawing represent many particles in the load. It's 1 unit of resistance, and in the first one, I have 2 units of resistance. In the same second one, I have 3 units of resistance. And in the third one, I have 4 units of resistance, or twice as much as the first one over here. So this needs to be changed to 1. The idea of current is how fast electrons are moving. So as soon as I connect the battery to from one side of the battery to the other, the charges start moving because there's a potential for them to move. And as if I don't connect any load, these electrons have no resistance, so basically they can move really, really, really quickly, causing a lot of issues and causing what we call a short circuit. To use that electric potential energy, I need to connect it to something. I need to be smart and actually use that electric potential to convert it into some other useful energy. So let's say I connect it to a load here. Let's say this load is a light bulb. And as soon as these electrons start moving, they bump into the particles here. And as soon as they start vibrating, the movement of these particles cause heat and light and maybe other forms of energy as well. But the movement here and how fast they move is the idea of current. So current is a measure of amount of charge. So how much charge is passing through a point per unit time, and it's measured in a unit which we call ampere and usually show it with the letter A. In this specific case, these little negative signs that I've drawn show many different electrons, and let's say they're 1 unit of charge, and as soon as I connect these units of charge go bump into these parts, and then they flow to the other side. The battery recycles these through chemical reactions, and this action continues on until the battery can no longer do any more chemical reactions. The idea of resistance here now, between the different ones, resistance is a measure of how much material can oppose the flow of currents, and is measured in a unit which we call ohms. So in this specific one, in the first one, you have two blockages. So as these, or two particles. So when the units of charge are moving, they have to bump into two things. So if they bump into two things versus three things versus four things, which one do you think will have a slower set of electrons or charges moving? Well, it would be the one with the least amount of traffic, because this resistance again is measuring how much this material can oppose the flow of current. So if it's more blockages or more particles that are on the way of the movement of charges, then it slows them down more. In these ones, as the electrons come in, they hit one, they kind of they're still forced to move because the electrons behind them are pushing them. So they transfer some of the energy, they get pushed, they transfer some of their energy into this one, and then they move. But they only have two different blockages that they're hitting. Whereas in this one, they have to do that 3 times, slowing down the entire lineup. And in this one, they have to hit it 4 times, slowing down the whole lineup of charges even more. So the current is how fast they move. So in this specific case, between the 3 different cases, current 1 is going to be the largest of them all. And then current 2 is going to be the second largest, and current 3 is going to be the slowest. And resistance 1 in the very opposite way, because we have the same battery or the same amount of force coming from the battery, will be the smallest of them all. Resistance 2 will be the second, and the largest one here will be resistance 3. I'm also going to add here, based on the definition of current, which is the measure of amount of charge passing through a point per unit time, it's saying how fast these charges can move. So amount of charge is generally shown with letter Q, and the time is shown by t. So the equation for I is the change in amount of charge over change in amount of time. Charge, we haven't talked about this too much, but 1 unit of charge is measured in units of coulombs, usually shown with letter C. And time usually is measured in unit of seconds. So I'll write the units here as well. This unit over here is coulombs. This unit over here is seconds. And as resistance increases, this current, so as resistance is increasing, the current overall is decreasing, meaning that there is less charge moving every second. And again, going back to this measure of amount of unit of charge passing through the point, it means that if I take a point in circuit anywhere, let's say I take this point, I'm measuring how many units of charge are passing through here. Per unit time. It could be minute, it could be seconds. Generally, it's measured in seconds. So if I have 2 units of charge moving through this point every second, then it means that the current is 2. If I have 4 of them moving, it means they're moving faster. It means that the current is 4. And let's say if the current here was 4 and the resistance was 2, in this one, because the resistance has increased to 4, it means that the current is now going to be twice as slower. So the current at this point, or any point in this circuit, including even somewhat inside the battery, is going to be 2 versus 4 in this one. So faster here, twice as fast the current, twice less of resistance here. We also need to talk about energy per charge, and this one is a little bit complicated and abstract, but it's one that it takes a little bit of time to really understand. So potential difference, typically shown with delta, delta meaning difference. V is typically a letter we use for potential, and E here is showing electric potential. So this idea here is showing the potential difference. So this one is electric potential, and this sign over here is showing that it is the difference. This is the difference between the amount of energy per unit charge of 2 points. What? So let's kind of talk about this in terms of how much electric potential the charges have through the circuit. And we're going to start with this one. At this point over here, we got a lot of negative. Basically, this side of the battery is very, very negative. This side is not as negative, meaning that the electrons want to be pushed out from this side, and these electrons want to get, well, as soon as they're pushed out from this side, because this charge is going to move this one is going to move this one is going to move this one. As soon as this one moves into here, gets recycled by the battery, and that action continues. So at this point over here, the potential for the charges to do work is the highest. And as they move through the wire here, we assume that the wire has no resistance. So they're not going to bump into anything. So they're not going to lose any of their energy here. But they start losing their energy as soon as they bump into a particle in the load. So here they're going to bump into this one, transfer some of their energy, slow down, and then they're going to move in and transfer the other part of their energy. And then from here to here, they no longer have any potential to do any work anymore because they're not going to bump into anything more. They're going to come in, they're going to get recycled, so they're going to gain potential to do work again. And then that patterns continue. They're going to lose some of it here, no more potential, and that pattern continues. We'll talk about the detail of that in a second, but I also want to talk about a term called electromotive force here, which is a little bit confusing, but it's not about the force, but it's actually about energy per unit charge. But electromotive force, typically shown with the letter epsilon, is the maximum energy per unit charge to move the charge through a circuit. And here we're assuming that there's actually no internal resistance in the battery. In reality, there is some. But if there's no internal resistance here, the maximum amount of energy required to per unit charge required to move the charges through the circuit, we call that EMF. Now that depends on a few things, and that's kind of the strength of the battery. Depends on the chemicals used inside for the chemical reaction, the concentration of those chemicals, and somewhat the temperature as well, and some other factors as well, but those are the main ideas there, or the most significant. Some things that don't affect that amount of energy or the amount of electromotive force is the size. So the size, if we get a bigger battery here, but we're depositing the same amount of electrons on one side, the charge difference is the same. And bigger battery means it will last longer, but it doesn't really affect the electromotive force or the EMF. So as the charges are moving within the circuit, they're going to gain certain amount of energy, and the maximum amount of energy that they're going to get is called the EMF here. They're going to get certain amount. Let's say in this specific circuit, which I've drawn as a circuit diagram here, they get a total amount of 24 joules of energy for every charge. So that is equivalent to 24 volts. So as the charges are coming, they're going to gain 24. That's the maximum amount of energy that they're going to get and use throughout the circuit. So they're going to get their 24. Now the electric potential here is about 24. They don't bump into anything until they get into, they start hitting the particles inside of the load. Here they're going to lose that energy. The maximum amount of energy that they've gained through the battery was 24, or their potential was 24. So they're going to lose all that 24, and they're going to come back and kind of regain that electric potential here and do that again. So this idea over here, or this type of graph, not always taught, is called the potential versus position on a circuit. And in this specific one, we're dealing with electric potential. I just haven't wrote electric potential here. And we're going to look at what is the potential of every charge to do work within a circuit at different positions. So at this position over here, or this position in the circuit, the charges are not going to bump into anything. So they don't really have any potential to do any work. So at this point over here, their potential to do work is 0. So I'm going to put that as a 0 potential. Once they go through the battery, now you have an electric field here. They kind of gain potential, which is the same amount as the EMF or the electromotive force, to do work. So each charge here gains about 24 joules of energy, meaning that they will have their potential to do work increases. To what exact value? Well, 24. That's the EMF. After that, from point 2 to 3, as the charges are moving, they're not really bumping into anything, so their potential to do work doesn't change from 2 to 3, and it stays as 24 from these 2 points. From 3 to 4 in this specific circuit, well, they start bumping into different particles here, and as they bump into each one, the ability to do more work keeps decreasing and decreasing and decreasing, eventually to 0 at point 4. So this is still 24, and at point 4 it's 0, so I'm going to draw that with a drop here. And then from 4 to 1, this is going to stay the same. From 1 to 2, when they go through the source, they're gaining potential, and this is often called a voltage rise because the potential to do work is increasing. And when they go through a load, this section is called voltage drop because the ability or the potential to do work reduces. Understanding the idea of how this works in different circuits is really essential in understanding how the details of every circuit works. So again, in terms of potential, the potential is the ability of the charges to do work. So at this point over here, they have a potential to do work because they're going to bump into different parts of the circuit. When they go through here from point 2 to 3, we can see that they don't really bump into anything, so their potential stays the same. Potential difference here is measuring the difference between the potential at different points. And it's usually measured using a device which is called a voltmeter. So if I connect a voltmeter in parallel here with my uh, between the 2 points in the circuit, with parallel with the source, between points 1 and 2, it will measure the potential here and it will measure the potential here and subtract them. In this case, it knows the potential here to do work is 24 and the potential here is 0. That's kind of here, and that's the amount of rise, potential rise here. So it will measure a reading of 24 at this point over here. If I connect my voltmeter at this point over here, then the reading here is going to be the difference between the potential at 2, which is 24, and at 3, which is also 24. And since it's constant, the potential isn't changing, the difference is going to be 0 volts at this point. The potential across point 3 and 4, if I'm measuring that, well, the potential to do work here is 24 volts, and it's once it bumps into pieces, it has no energy left to really deliver anymore. So it's going to have 0 potential energy to do work here. So this reading here is going to be 24 minus 0 minus 24. I'm just going to take the magnitude or the size of it. It's going to be a reading of 24 volts, but at this time it's a drop because it goes from a higher value to a lower value. And that difference again on our graph is from this point to this point. And finally from 4 to 1, I'm not going to draw that one. We have 0 potential here, 0 potential here, and the difference there is 0 minus 0, which is 0. So that's what the potential difference does. In our case, we are going to mostly work with potential difference and not really worry as much with potential. Knowing that idea is extremely important, but the difference is really what we care about, because when the difference is 0, it means there's no change in energy in the circuit. But if there is a change, it means it's either gaining certain amount, those charges are either gaining some energy from a source or they're losing some energy from the load. Finally, we're going to discuss the relationship between everything we've learned, the potential difference, the current, and the resistance. And we're going to do this with having two different circuits here. One is these two batteries are pretty much the same, and this battery is connected to a resistor which has two major set of particles. So this is not just one particle, many particles. This one has more, twice as more. This has 4 set of particles. And before doing anything, we're going to talk about the potential. Note that at point 1, the charges are not going to bump into anything before they get to the battery, so they will have a potential of 0. And then as they move through the battery, they gain the maximum amount of energy they can spend later, and that's about 24 joules for each charge, leading to a value of 24. From 2 to 3, they don't really bump into anything, so they're neither gaining energy or losing energy, so their energy stays constant at 24. And then they start losing some of that energy, and their energy drops back to 0 from point 3 to 4 as they bump into the particles of the resistor or the load, and they transfer their energy to these particles over here. And from 4 to 0, that energy is 0. The change in energy is 0 and the total energy is 0. And I'm going to write the number here. This is 24 volts just so that we know. Now that doesn't change in this circuit, it's the exact same idea. The charges are coming in, they have 0 potential here, they gain a potential to do work, 24 to be exact. Here, one other idea that I want to talk about before I forget is the idea of conservation of energy. And this idea says that energy cannot be created or destroyed, it can only change form. And that form is either from object to object or from type to type. So at this point, when the charges are coming in, they have zero electric potential energy. When they move through the battery, at this point over here, they gain electric potential energy. And that kind of turns into kinetic energy here. And that electric potential energy goes into kinetic energy. That kinetic energy the kinetic energy of the electrons here transfer into the kinetic energy of the particles here. So the kinetic energy of charges into kinetic energy of the particles in the load. So they're transferring their energy here. And that kinetic energy there is being converted into other forms. So that energy is not being created or really destroyed. It's only being transferred. And that kinetic and like when the charges are coming in, is the chemical energy that's doing that. So this idea is extremely important. Now going back to what we were talking about in terms of the energy here, in this circuit as well as this, the energy transfer doesn't change because as the charges are coming in, they gain a potential to do 24 volts or 24 joules for every charge. Same energy, 24, they're not bumping into anything, but as soon as they get here, they start bumping into things. And that becomes important, and it kind of creates this relationship between the potential difference, current, and resistance. Let's think about this in this major idea. As these charges are moving in this circuit, they have two resistors to kind of hit. And in this, two particles in the resistors that they have to hit. And in this one, they're getting the same amount of energy. So every charge gets the same amount of energy, but they have to hit 4 different particles. Hit 2, hit 4. There's a difference there. And what does that difference do? Remember, the total amount of energy they're using is exactly the same. However, in this one, they only hit 2 things. So if a charge is moving and it has 24 joules to spend, when it's hitting 2 different particles, on average here, it spends 12 joules here, half of it here, and 12 joules here, which is the other half. So 2 halves here. In this one, when they're moving, they have to spend their energy into 4. So the maximum energy they have is 24. They hit 1, 2, 3, 4 different particles, meaning instead of spending 12 joules on each, they're spending 6, half of the energy. How does that happen? Well, think about it this way. If you have a particle moving extremely, extremely fast, and it hits another particle, it transfers a lot of energy. And if the object is moving slower and it hits a particle, it transfers less energy. So in the first one, if it's spending 12 joules of energy upon the collision versus 6 joules, it means that this one was probably moving twice as fast. Well, that's exactly what's happening. Remember we said that if the resistance increases, the speed of the charges decreases. Well, how much is it decreasing in this case? Exactly by a factor of 2, because this one has 4 different particles that they have to hit. So as they hit them, they slow down, and then they slow down the entire lineup. And you can imagine this on a highway. If there's a long distance where there's obstacles, the traffic slows down a lot more than if it was just a very, very short amount. So as these charges are moving, in the first one, they're in this one they're moving twice as fast as this one, and if they're moving twice as fast, they have to hit. Every time they hit each particle here, they're transferring twice as much energy to these particles than they are in this one. Transferring 6 joules of energy to each, transferring 12 joules of energy on this, moving twice as fast here and moving twice as slower here. So the idea here is the current is is the ratio of the potential difference to the resistance. In the first one, the currents, I'm going to write this down over here, the currents is equal to the change in potential difference. So remember, the potential difference between this point and this point where the energy transfer is happening is 24, because we have 24 joules here, and then we have 0 joules over here. So I'm going to write this as delta V over R. And in my first one, I'm going to write R1 and I1. The total amount is 24 and the resistance is 2, meaning it's 12 amps here. In the second one, I2, for the second circuit, my God, delta V, this is V1, this is V2, they're the same, R2, and I have same amount of energy that's being lost here between here to here. Again, it's the same amount. I'm losing 24 joules of energy, or 24 volts, because it's per unit charge. Resistance here, however, is 4, and that would mean that it's 6 amps. So this is kind of saying, oh, on this circuit, the particles have to move twice as slow in order to transfer less energy to each particle. They're still spending the same amount of energy throughout the two resistors, which is exactly 24 joules, or we can per unit charge, so 24 volts. However, they're moving a lot slower in this one and a lot faster on this one. So that's the main idea of why this relationship works, where current is a measure of the potential difference over the resistance, and that's why as resistance increases, the total blockage is increasing, slowing down the charges. And if they slow down, it means that even though they're getting the same amount of energy, they can't really transfer as much energy to each individual particle as they did in the past. That's why their speed decreases, so they can transfer the exact same amount of energy. And that is the relationship between potential difference, current, and resistance. I know that was a lot of information, but I hope it was useful to you and that you learned something. I hope that you keep learning and that you keep changing the world in a positive way.